Alright, so for the last beam example, we have chosen the overhanging beam to calculate our reaction forces and shear and moment diagrams. I've already marked the two supports, which is pin support at point B, which has two reaction forces, FBX and FBZ, and a reaction force at point A, FAZ, which is the roller support reaction force. We also mark the positive directions for our forces, also known as the axes. So let's start from calculating our reaction forces. First of all, we can see that the FBX reaction force is equal to 0 because we have no horizontal loading. Now let's calculate the moments at point A to calculate the vertical reaction force FBZ. So the sum of moments at point A is equal to 0 in order for this structure to remain stable. Since we have marked positive moments to go clockwise, the distributed load of 2 kilonewtons per meter will give us a negative moment. So it's -2 times the distance of how much we have this distributed force times the distance times the moment arm distance. So -2 times 3 times 1.5. For the next moment we have this 9 kilonewton meter moment, and since this moment goes clockwise relative to point A, this is a positive moment, so +9. Next we have our 2 kilonewton meter moment, and since this goes counterclockwise relative to point A, this is a negative moment. Then we have our unknown, which is FBZ times its moment arm, and since this is this moves the beam counterclockwise, this is a negative moment, and the moment arm is equal to 4 meters. And then finally we have this 2.5 kilonewton force, which creates a positive moment and has a moment arm of 8, and this whole equation has to be equal to 0. Now the reason why we didn't add the 3 kilonewton force right at point A and the reaction force FBX is because these forces have no moment arm, therefore they don't create any moments. So now let's calculate how much is FBZ, and we get that FBZ is equal to 4.5 kilonewtons. Now to calculate our final reaction force FAZ, let's use the sum of forces for the beam in the Z direction, sum of forces in the Z direction, and this has to be equal to 0 for the structure to remain stable. And now just let's add up all the forces and reaction forces and calculate our unknown reaction force. So firstly we have our 2 kilonewton per meter distributed load times 3, because this is how much we have this load, plus the 3 kilonewton force, plus the unknown FAZ, which goes into the negative direction, so it's actually minus FAZ, minus the reaction force FBZ, which is 4.5, plus the final force 2.5. And now let's calculate the FAZ is equal to 7 kilonewtons. Now let's move on to calculating our shear force diagram. Since the first force is a distributed load, it will give us a linearly increasing line in the negative direction. So let's calculate the sum of what this distributed load will give us. So it's 2 times 3, which equals to 6 kilonewtons. And since this force pushes against the beam with a positive direction force, it creates a negative shearing within the beam. So we draw our shear force diagram in the negative side of the beam. Next up, we have this 3 kilonewton force, which creates a negative shearing within the beam, and our reaction force FAZ, which is 7 kilonewton force, which creates a positive shearing. Minus 3 minus 6 is equal to 9, and plus 7 is equal to minus 2. So next we have nothing until our second support, which gives us the reaction force FBZ, which gives us a positive shearing within the beam. So 2 plus 4.5 will give us minus 2 plus 4.5 will give us plus 2.5 shear force. And then we have also nothing up until the last force, this last 2.5 kilonewton force, and since this will give us a negative shearing within the beam, the sum will be 2.5 minus this force 2.5, which will give us 0. Now let's move on to calculating our moment diagram. First of all, we have to we'll use the area method, the integration method, which is to calculate the areas, the shear force diagram areas, and add moments and look the shape of the graph. So first off, we have this triangle, minus 6 times 3 divided by 2, which will give us an area of 9 kilonewton meters. And since this is a linear line, and when we integrate a linear line, it will create an exponentially growing line. So 9 kilonewton meters. Next up, we have this rectangle, and we also have to make sure that we count in the moments on the beam, the 9 kilonewton meter moment and the 2 kilonewton meter moment on the beam. So let's divide this rectangle into 2 rectangles, and we will get minus 2 times 2.5 minus the moment 9, which will give us 14. Since a rectangle is a horizontal line on the shear force diagram, it will give us a linear line on the moment diagram. Now let's subtract. Now let's add this 9 kilonewton meter moment to our minus 14 kilonewton meter shear force, and we will get 5. Next up we have again a rectangle which will give us a linear line, and let's calculate the magnitude. So 1.5, which is the distance, times 2 will give us 3, plus 5 will give us an 8. So a negative 8 kilonewton meter moment. And now we also have this moment on the beam, the 2 kilonewton moment, so the moment diagram will jump up, because this is a counterclockwise moment. It will give us a negative moment, and we'll 8 plus 10 plus 2 will jump up to 10 kilonewton meters. And finally, we have this huge rectangle, this 4-meter rectangle, which has the height of 2.5 kilonewtons. 4 times 2.5 kilonewtons will give us 10 kilonewton meters, and when we subtract our 10 kilonewton meters that we have on the moment diagram, we will get back to 0. And again, this is a linearly decreasing line because the shear force diagram has a horizontal line. Now that's it for this video. I hope you enjoyed. If you have any questions, then comment them down below, or if there's anything mechanics related that you want to see next.